Full disclosure, it's been a minute since I had to stand up in front of a group and pretend like I knew what I was doing, so be gentle. By a minute, I'm being generous. If you grew up in my mom's kitchen, you knew all about the Leidenfrost effect. She just didn't call it that. She called it making pancakes, because she'd get the griddle ready and she'd throw some drops on the griddle, and if they boiled away, you had to wait. If they danced around like little ballerinas or something, then you could ladle on the batter. So what I'm going to talk about, I'm going to go briefly into some of the models that they use for liquid and solid interactions, so we can contrast the Leidenfrost effect with those. Then we'll look at the thermal Leidenfrost effect, the classical Leidenfrost effect that's driven by temperature. Look at some examples, some videos of that in action. We will do a very, very small math slide. That was funny. Okay. And then I'm going to do the same thing for the fizzy Leidenfrost effects. Again, just a little bit of math. Some examples. Then I've got a comparison of the Cassie-Baxter state and the Leidenfrost states, because they look very similar in a hydrophobic environment, just to show you, what the levitation looks like and how they measure that. And then we'll talk a little bit about very little bit about a couple ideas for practical applications that people have had, specifically the folks that wrote the paper that I'm mostly referencing. So the ideal model on the left assumes a perfect surface, completely smooth, polished, no defects, which obviously doesn't exist in real life. It uses Young's equation. Box in the lower left shows Young's, Wenzel, and Cassie-Baker's classical equations. And it describes the contact angle strictly in terms of the surface tensions associated with the three contact lines, the liquid vapor, the liquid solid, and the vapor solid, right? The Wenzel model in the middle also describes a surface, but it's in which droplets can penetrate those rough edges. So that leads to very high adhesion, high friction, that sort of thing. It characterizes contact angle using the same Young's contact angle that's derived from that, but he adds a roughness factor in. I don't know how that works. And then finally, the Cassie-Baxter model describes a rough surface that's hydrophilic. So instead of wetting the insides of whatever roughness feature is on there, crenellations in this case, it sits on top of the surface of each one of those, trapping air underneath it. So it decreases the surface, or the solid to liquid contact, and increases the vapor contact. The equation for the contact angle for her takes into consideration the angle and the surface that the liquid is touching, because it could be touching multiple surfaces. The wiki page's a good reach. The classical Leidenfrost effect, God bless Wikipedia, because all things flow from it. It's a physical phenomenon where the liquid is actually generating a vapor layer due to the very high heat of the substrate or the surface that it's sitting on. And that vapor layer that is generated from the liquid itself insulates the droplet itself so it doesn't immediately boil off, and it levitates over the surface so long as it can basically fuel its levitation via vaporization. Named after German doctor Johann Gottlob Leidenfrost. If you look on the internet, you can find another guy that basically described the effect much earlier than him, but he's the guy that actually wrote it up and published. So just goes to show you. Was it publish or perish? These guys are all dead, so it didn't do them that much good. Some of the properties, as you'll see later, because the droplet only really ever comes in contact with the full solid surface at the end of its life, when it almost immediately, vaporizes. There's effectively no wetting, especially absolutely no wetting during the actual levitation part of its lifetime. You get near zero adhesion and near zero friction, which leads to extreme mobility. You'll see on one of the slides a little bit later where they actually use a pen to hold the Leidenfrost drop in place so they can do measurements on it. Because otherwise it just, you can't place it so exactly that it will sit unless you're using some sort of curved surface to contain it. And the vapor layer itself provides excellent mechanical and thermal insulation. I'll show you a picture of cooking an egg with this later. There are a couple of shapes involved with the Leidenfrost state. The one to the far right isn't a shape, it's a block of ice, dry ice. But you basically have a quasi-spherical state, and then as you pass the boundary where the surface tensions and the what am I trying to say? Inertial forces balance, gravity starts taking over, and you get a flattening effect. They call that a puddle, or I forget what the other name they use for it is. And on the right-hand side, they just show this is a small disk of dry ice, and you're actually getting the same effect, but instead of via vaporization, you're getting sublimation to create that vapor layer. Oh, and I did not mention, but I will, that layer on the bottom for the thermally driven Leidenfrost effect, it's got a characteristic thickness of about 100 micrometers. So on the left is a Leidenfrost star. I didn't go into very much about this. They didn't talk about it in the paper, but I thought it was an interesting effect. They've been observed with as many as 13 points. They arise due to the rapidly moving vapor layer underneath that flows up and ends up shearing the droplet itself. And the resulting ripples travel through the drop. They cause pressure oscillations in the vapor layer underneath, and the feedback from that causes the puddle to take on characteristic modes based on the frequencies of those ripples. So, really? And then on the right,
John, that's pretty much 10 minutes. We can go into the Q&A.
Oh, shall I go to the Q&A?
Well, no, I mean, we'll go into your Q&A period.
Okay.
We'll give you 2 or 3 more minutes.
Okay. Cooking the egg using the Leidenfrost effect. Same deal. My wife would kill me. That pot has had it. Okay. And this is the very small mass. Basically, I will.
Oil, isn't it?
No, that was egg on a completely oilless surface, and it's actually generating the moisture in the egg is generating that vapor layer. That's what I mean. You look at that thing, and it's like that thing should be burned to a crisp. Not. I'm going to skip the maths. I didn't realize it was going to take this long. Just real quick. Yeah.
मेरे समझ से तो इसका हाथ अभी तक पूरा जल जाना चाहिए और हड्डियां दिखनी चाहिए. तो चलिए इसके बारे में हम जानते हैं. इसका
But
मेन
it makes it very, very impressive. So, yeah, it's used all over the place. You don't know you're using it, but you didn't die, so it must have worked. The fizzy Leidenfrost effect, basically, this is a quote from the authors. But basically, the Fizzy effect just taking advantage of the off-gassing of a supersaturated carbonated liquid. So it's continuously generating its own vapor layer with that in the absence of heat. Sure. Well, I postulated that he's carrying the woman because she doesn't want to burn up her new shoes, but I'm sure there's another reason. Yeah, I don't know what the stomping is about. Anyway, they attribute that to the sweat and stuff and the vapor layer that's generated when you're going over the coals. I'm not willing to try that myself, but yeah, and if you don't sweat much, don't do that. Basically, this is the comparison of the Cassie-Baxter to Leidenfrost states. Just real basically, take a look at the top, which is the Cassie-Baxter, and you can see that it's fully engaged with the surface. You can't see the crenellations and stuff like that at this resolution, but if you look directly under it, that's another image of the Leidenfrost effect, where you can see a thin bit of light coming underneath, showing the actual levitation. And then they also measure it in D and H using, I can't remember the name of it, interferon, no, thank you, and the interfringes, or the interference fringes from the bottom in H show that it actually is levitating as opposed to having contact on the tops of the rough surfaces, as you see in D. Life of a fizzy Leidenfrost droplet. The only thing I want to show you here is how much smaller the actual layer ends up being at the beginning, which is on the order of 2 to 5 micrometers opposed to the 100 micrometer size in the temperature effect. Again, I'm going to skip the math. Main differences that I pulled out of this were that you've got a Marangoni effect inside the droplet itself. It's generated by the temperature differential between the vapor layer, where you've in the liquid you've got boiling conditions, and at the top you have a few degrees less than that. That doesn't exist in the fizzy Leidenfrost because it's all happening at ambient temperature. The classic Leidenfrost drop doesn't survive the process, whereas once you've depleted the CO2 concentration in your water droplet for the fizzy drop, it hangs around and goes to a wetting condition that's dependent on the hydrophobicity of the surface that you're using for testing. You've got orders of magnitude decrease in thickness of the vapor layer, and much slower speeds on the order of like 10 times for the fizzy one as opposed to the other one. And obviously you have a time-dependent vapor flux, since you've got an ever-decreasing concentration of CO2. This is a video I would recommend just watching. It's from the same guys that actually wrote the paper, and they basically, okay, I'll show you a little bit of it because it does go on. But it basically shows you the life of that speeded up a bit. So you can see when it first starts off, you've got interference lines, and then over the life, you keep getting more and more contact that's going radially inward until it reaches a Cassie-Baxter state. And of course, they bounce exactly like that. I'm joking, I don't. But they go through and they explain what's happening and that sort of thing. So it's a very entertaining video. Another video I'm going to skip. Basically, you want to see that? Okay. This is really cool. Full disclosure, I am not sure whether this is the temperature driven or the fizzy effect, because this is aluminum, so it could be sitting on a hot plate generating it that way. But basically what they've got is microtextured surfaces where they have milled in little grooves, asymmetric grooves, that drive the direction that it basically manipulates the vapor flux, okay, so that it goes out one side and not as much on the other side, so that it can actually force it to traverse a maze. Yeah, well, it's got its own propulsion. All the maze is doing is working on the direction. It's affecting the direction, but it brings its own propulsion to it. So there's no external mechanism, you know, they're not blowing those things around or anything. That motivation is coming directly from the vapor flux itself. And they had a couple ideas from the paper, maybe a seagoing hovercraft using the really low boiling temperature of dry ice or other things like that for the motivation power. And obviously the cushion that you're riding on. Unfortunately, both of these things were embedded videos, and since I'm not doing it from my computer, I can't play them. But if you look up the paper, they have links to these various things. And the second one was really interesting because if you look at all these bubbles on the top, these are actually oil droplets. And as this thing goes around, the difference in surface tension between the drops and the water and the ice and stuff basically collects these things. So at the end, you've got this guy and all of the oil surrounding it. So. Okay. That was wrapped up. Here are the citations. Thank you.
One question for Don.
Yes. Good, because I don't actually know anything
I
else.
might have missed it. Can you explain fizzy effect briefly again? I didn't understand fizzy.
Oh, the fizzy.
It's to do temperature gradient, but
Yeah. So basically, for the you've got the classical effect was driven by temperature, right? Okay. Yeah. Let's.
I can stop here.
Let me give you this.
You can yourself.
Oh, okay. You wanted to know about the fizzy droplet effect?
briefly, like.
Okay, so real quickly, all that's happening with the fizzy droplet effect is instead of generating a vapor layer by vaporizing your droplet material itself, they take still water and they supercarbonate it. Basically, in this, you can use other things, but other gases, but they supercarbonate with CO2. So it's constantly off-gassing. So as soon as you drop that droplet or remove it from its container, your flux, or I'm sorry, your concentration continues to go down. So
Off gases in all directions, though, right?
that's the other difference. There are a lot of differences, but one of the other differences is they showed that in the classic Leidenfrost effect, the vaporization is happening only at the basal layer of the droplet, whereas in a fizzy water experiment, you have off-gassing across the entire surface, but it's very much slower than the vapor layer that's being generated by the heat. So that's one of the reasons you get slower. What am I trying to say? Slower velocities or flux. Thank you. But that's also driven by the order of magnitude smaller vapor layer itself. You don't have the area that you do for the vapor to escape.
All right. Homework 3. I think I said it in next Friday. It's on the grade scope, but I think it's not this week, but maybe in two weeks. And we should pretty much next 2 or 3 lectures we should be able to give you enough practice with what we call similarity solution. roughly 2 weeks. All right. Okay. So Monday of Thanksgiving week. It's funny. I've been in Georgia Tech for many years. We originally had school on Wednesday, the day before Thanksgiving. And of course, people don't want to do that. Okay, so for international people, Thanksgiving is like the American holiday that like between Christmas and Halloween. And but anyway, we used to have school on Wednesday. We really don't like that. Now we don't have school on. Now we have school on Monday and Tuesday. But actually, I won this award, so I have to go to DC, and I can't come back. I don't think I can come back on Monday. We could do the lecture online at 9:30, or we could just do like an extended office hours. What do people prefer?
I think you said this as a presentation day.
Oh, okay. Oh, really?
At least the sign up for the
Okay.
presentation said this Monday was presentations.
Oh, we won't need that many because there's still 3 classes after. So I think maybe we'll just be okay. We'll just cancel class then. So have an extra Thanksgiving.
All you gotta do is convince my Christians professors to do the same thing. I'm golden.
But we'll have, I think people still need the office hours because we'll still maybe have homework due at some point by the end of the semester. So around that time, I'll have a group me. I'm guessing when people want the office hours, they don't want that at 9:30 in the morning. I'm just guessing based on the preferences. So as the day comes, we'll figure it out. But all right. So we're going to do our first fluid mechanics problem today. I mean, last time, let's just review a little bit what we did last time. Is that what we did last time? Yeah. Why is it so big? All right. All right. So we had talked about unidirectional flows. Unidirectional flows is defined by basically flows are going in a certain direction and you have some boundary. Okay. So usually flows are in the x and y directions, but here it's just going to because you can align the coordinate system how you like, we'll just have the flows going in the x direction. And we said unidirectional flows has this nice property that first Navier-Stokes equations has this term that says the velocity dotted with the gradient of the velocity. Now, gradient of velocity, let's say if we had a wall here, there is some wall, the gradient of velocity would be normal to this. And if u is, perpendicular to that, that means this is going to be 0. So that's why we have no nonlinear terms in Navier-Stokes. And the reason why Navier-Stokes was so treacherous for people to solve was because of this nonlinear term. But if you have a unidirectional flow, you don't have that nonlinear term. And this whole homework is going to be on basically unidirectional flows. Okay. So we worked out that the only momentum component you care about is momentum in the x direction. And we had basically the time dependence here, the time dependent change of the horizontal velocity, any pressure gradients, like we saw if you have a tube-based flow, that's what's pushing fluid through, and any contributions of viscosity from the boundary. If the boundary is stationary, as it was for the tube, then you basically, viscosity at best can just slow you down. But the problem we're going to do today, and I think the problem in the homework, is driven by the wall. For example, Couette flow. Couette flow was the top boundary moving to the right, and that was driving the flow. Okay, so that's what we're going to be doing, a special case of unidirectional flow, but we're going to do time dependence. So this is our first unsteady unidirectional flow. Unsteady just means it's a function of time. We're gonna do 2 problems, but this is going to take. I think we can probably get a lot of it today. We're going to do the Rayleigh problem, first done by Mr. Lord Rayleigh, and then we're going to do the oscillating flat plate. And we're going to do the second one in much less detail because we're going to have to do the gory detail for the first problem. And I think we'll do some group work today too. All right, so probably next time. All right. So the Rayleigh problem. And Rayleigh had actually 3 problems. I mean, he had a lot of problems that he did. But these 3 are sort of the canonical teach people how to do unsteady flow problems. So they call this, I think, Rayleigh's first problem. I think in the homework, I gave you Rayleigh's third problem, which is oscillation. Okay, but it basically looks like this. We have a bottom plate. Okay, so we have these axes, x and y. Physically, imagine this bottom plate's infinite. It's like a plane, and basically at time 0, it's stationary, but at time, basically, as soon as time 0 passes, it moves to the right at velocity v. Okay. So physically, you imagine the whole fluid stationary. In the beginning, it's going to move to the right. So that means every cross section, because it's infinite in the x and y directions. So imagine it kind of looks like this. It's like this plane. At every single x and y, I'm going to figure out a velocity field, and it's kind of going to look like this. Basically, initial time you're going to have some velocity here. Later times you're going to get farther, and later times you're going to get more velocity. But basically, as time goes on, any distance from the plate, I'm going to feel the plate moving. But it takes time for that information to get there. And that velocity distribution is constant, and it doesn't depend where I am on the plate because that plate is infinite in 2 dimensions. Okay. All right, so and initially quiescent fluid, we begin to move planar lower boundary at speed v. All right, and so Rayleigh said, hey, I'm going to tell you what the flow looks like as a function of time. And out here we got some kinematic viscosity. Sorry, not kinematic. That's dynamic viscosity, u. All right, so so this could be an important problem if you're like a bacteria or something like that and you feel a bottom plate moving. I mean, if you're really small, everything else is considered infinite because you're never going to swim to like the edge of the Georgia Tech swimming pool. You're always going to be stuck there. So it could be basically how information is transferred from the boundary to you. So let's make a few notes about how we're going to solve this problem before we get into the details of even the boundary conditions. So the domain, we call this domain unbounded. Imagine it's like an infinite space that's just cut in half. So everything above this exists. So this velocity, since the domain is unbounded, the velocity field evolves continuously. So it's very different from if I have 2 walls. You imagine if I'm like a meter away from the plate or 10 meters. At some point, if I get farther and farther away, eventually I'll get hit by this, passing velocity field. So there's no steady state in this problem. It just the way the information gets propagated outward. So you're going to have to get something as a function of time. You're not going to assume, it's steady state. Y equals infinity is more like an idea. Any finite distance, certainly, it'll get there. But it takes an infinite long time to get to infinity. Yeah?
What do you mean by domain is bounded?
Unbounded. Domain being bounded would be like, I don't know, if you were like in a tube, like we had last time. I think, for example, the homework, you're going to do, I think it rotates Infinitely long cylinder, which is rotating with constant angular velocity omega, at time equals 0, the cylinder is suddenly brought to rest. Figure out the velocity profile. So that one basically is bounded because like you have an infinite amount of fluid, but it's bounded on both the top and bottom. Here it just like goes on forever. All right. Like the Couette flow problem, there's no pressure gradient. So unlike Poisson flow, you're not basically sucking the straw to get the boba tea. This is driven by motion of boundaries.
And you just have the one bound moving plate on the bottom.
Yeah, that's right. Yeah. So, for example, in the x hat direction, dp dx is 0. Okay. So that means from what we reviewed from last time, because this is a unidirectional flow, like the boundaries here, and I got my velocities in the x direction, that means the governing equation has just 2 terms. Just 2 terms. How hard could the problem be? All right, it's just these 2 terms. Y. Distance from the top plate, different distance from the bottom plate. And we're assuming we're basically just solving it in this direction. I know it's infinite in that direction, but you imagine at every single position z into the page, you're going to get the exact same profile. So we just have these 2 terms. Because there's only 2 terms, this is why people use the kinematic viscosity, because then you can just have to write 1 constant instead of 2 constants. Mind your handwriting. All right, so this one's called nu, the Greek letter nu. There's probably some sorority with a nu in it. And that one's called mu. But do not call them v or u. You're going to get very, very confused. Nu is kinematic viscosity. And that's equal to mu over rho. All right. So this is the governing equation that we're gonna solve.
So what happened to the rho?
I divided both sides by rho,
okay.
and then I have this new constant, which is nu, which you often see in the Reynolds number because the people want to write 2 variables. But physically, if I've measured the density of a fluid, I've measured its dynamic viscosity, I know what nu is. It's not new information. It's just a shortcut of notation. All right, so that's our governing equation, and let's see. This is like all Navier-Stokes, this is a time dependent. You have initial conditions because time matters, and you have boundary conditions because space matters. So let's just write it out so people know what I'm talking about. Initial conditions. All right, so we said basically, all right, so I'm going to have this notation, u of y comma t, okay, because I only care about the distance from the bottom plate, and I care about time. So initial condition means that t is equal to 0, and that's going to be equal to 0 for all y, right? That means it's quiescent, which means that not moving. Okay, so stationary in the beginning, and now the boundary conditions. Let's just write it out for the first time so people understand boundary conditions. I'll be using the BC-IC notation probably for the rest of the next lectures. Yeah.
Means not moving at the beginning?
Yeah. So u of y comma 0, this basically means that t equals 0. That means the velocity is 0 for all y. So at t equals 0, velocity equals 0. Yeah. That's what this funny notation means, because this is a the velocity depends on the position and time. So that's why you have to have y comma t. All right. The boundary conditions says that basically when you're at y equals 0 at the bottom plate, that velocity is set by the plate. So that's v, and this is for all t greater than 0. So basically, after time equals 0, that plate instantaneously starts moving. It doesn't even have a ramp up. It just goes from 0 to really fast. So you can imagine this solution is true in the case that you're looking at time scales far from whatever acceleration time of the plate is. So this is the first boundary condition, 1 and 2. Is I think what Felix mentioned, or maybe Cedric. Basically, as I go far from the plate, if I go far enough away, I don't even know the plate's there. That's basically the idea. Far enough from the plate, there's somewhere that it's quiet, that the fluid's not moving. I just got to go far enough away. All right. Okay. So, yeah.
Say that the gradient of velocity in the y direction is no longer changing at infinite.
I've heard of that condition before. As we go through this problem, we'll see if that works. You said that the gradient is du dy is equal to finite or 0?
0 at infinite.
Yeah. They're saying different things, though, because that's saying that basically u could be some constant value far away. And physically, I would say that's not the case here. Because if you integrate this, you get u being constant value. Because we know u was 0 to start with, so it has to be u far enough away. So I feel like this condition is somehow stronger. But I think some problems, they can be exchangeable. When we do this, let's revisit that and see if that would actually still work. But I don't think you certainly couldn't have both. Only one of those would work. Okay, yeah, Raj made a good point. All right, okay, now first a few words about this. So this is a PDE problem. So this is a PDE problem. So of course Navier-Stokes is a PDE problem in terms of y and t. Now, remember I gave you the 5-step plan for how you would solve problems in fluid mechanics? I guess if I were a better teacher, I would have given you a problem that I would start with the problem that 5-step would actually works. But this first one I'm giving you is a counterexample that you cannot non-dimensionalize this problem. Can anyone say why we can't non-dimensionalize this problem? Yeah, that's exactly right. So the problem is all those ones we did last lecture were like flow in a pipe, flow between two plates, co-ed flow. Those had a given length scale due to the space. But Rayleigh said, hey, let's just have no length scale. It is infinite plate. There's no length scale that you can think of really readily. It turns out there is a length scale that has to do with the diffusion length, but that changed with time. And we'll see how that emerges. So because anytime you have a problem that's like infinite in dimensions, there's no length scale, and you can't non-dimensionalize. So and remember when you did non-dimensional analysis, the non-dimensionalization for the homework, or you're going to do that this weekend, hopefully. You had to have a length scale because you had either a length scale or a time scale or a velocity scale. We have a velocity scale, but we don't have any of the other two. So you can try, but you're not going to get much progress because you have all these derivatives that you need to have a length scale. So luckily, for problems that are infinite and bound that have no length scale, the mathematicians have found that this is called a similarity solution. And there's whole books, and like it's a whole, like if you take PD PD, I keep on saying that, I might as well tell you what it means. Partial differential equation. There's whole sections on how to do this. The nice thing about similarity solutions is that they actually do mean something too. It's not just a mathematical trick. Physically, the way you solve the problem gives you insight into why that problem is the way it is. Similarity solution, basically, so similarity solution means, in general, you expected something like this. U to be a function of the variables independently, nu, y, t. Here, similarity solution means U is function of groups of variables, of groupings of variables, rather than the each variable separately. Oops. They do a lot of similarity solutions in heat transfer, do they? Yeah? Okay. All right, then I won't. But you basically, how do you guess what the similarity solution is? This is where you use Buckingham's pi theorem. All right. So if you remember Buckingham's theorem, dimensional analysis, which you'll do for the homework, says that, hey, we don't care about the Greek names, we only care about the units of these variables. So first we notice so in the governing equations, rho is unimportant. Physical, and therefore we're not going to consider units of mass.
But isn't it used to define kinematic viscosity?
Okay, let's review for a second. So nu, I remember nu by the Reynolds number. Reynolds number is UL over nu. The reason they call it kinematic viscosity is because kinematic means there's no forces involved. And in fact, the units of kinematic viscosity are length squared over time, because it's cancelled. Because basically, the density, physically, the density contributions got canceled out with the dynamic. The mass got canceled out from the density and the dynamic viscosity. So you only have kinematic viscosity. All right. So we don't have to care about mass. So this is point one. So we're not going to basically, you remember you do Buckingham's theorem, you usually consider MLT as the basically possible different dimensions. It means we have to just think about L and T. Okay. The other thing, let's look at our variable list. We've got the velocity of the fluid, and we have the velocity of the plate. Well, that's an obvious one you want to use. Because they have the same units. So U and V are linearly related. So we're going to think of U divided by V as the relevant physical variable. And I think this makes sense, because you can think about how fast, if you ask how fast is the fluid moving, people are going to ask, well, how fast is the plate moving? Now, for the rest of it, that's where we got to use Buckingham's theorem. I think this is a good time to see at your seats if you can use Buckingham's theorem for those variables, and if you can't, we'll do a quick exercise to do it together. So use Buckingham's theorem and figure out what the remaining pi group is. Yeah?
In this second part,
Yeah.
U is the position and V is the velocity.
Oh no, u is the velocity of the fluid is a function of y and t, and v is the velocity of the bottom plate.
Oh.
Yeah, that's v is like a constant. So we're gonna do. What time? We started this. Not start. Oh, we still got a half an hour. All right. I also want to do a little bit of group work because we have to change the PD into an ODE, and it's just too lonely to do it by yourself. So, do people want the little whiteboards, or people just want to like?
Oh, you cut your variables and then you cut
Should I get the little whiteboards?
units.
Would anyone want one?
Subtract one from the other to determine out.
You're fine with your notes?
Divide and multiply everything by like point and time scale. Let's get rid of all the units that are attached to it. So, kind of similar to what we did earlier, I believe. So I don't know which is
All right. Let's raise your hand if you know what if you want to review Buckingham's theorem. But raise your hand if you've heard of Buckingham's theorem. All right.
Oh, if you have or haven't?
Have.
Yeah, no, I can get that.
All right. Okay. All right.
I don't keep it around up here.
Okay. Buckingham theorem. All right. Buckingham. He said basically, he says, how do we solve this problem? This problem of how do you figure out how u depends on these variables? And he said, hey, I don't need to care about physics. I just need to care about the actual dimensions, the units. And that's why they call it dimensional analysis, because you don't have to use anything except the dimensions. So what we do is write u, v, what were the rest of them? Nu, y, and t. Nu, y, and t. All right. Buckingham theorem says, the first thing you do is write the units of everything. Okay, so units. And we use basically the possible units for Buckingham pi theorem are mass, length, and time. There's some places where you do force, length, and time, but let's not talk about that. All right, so see if you can write at your seats, make a little table here, what is the units? And please do not use SI. The whole point of Buckingham's theorem is that we shouldn't be using like the arbitrary dimensions, because if you're in, I don't know, you're in France, you use meters, but Americans, we like to use feet for some crazy reason that no one else can understand what we're talking about, but we're using feet. So velocity, what's the units? Yeah, length per time, good. And I gave you this one. This was length per time again. Nu, I think I wrote it up there because centric gas, length squared over time. What's the units of y? Length and time, good. All right. So, and Buckingham's theorem says, he tells us that basically m is equal to the number of variables, and n. So I think I can extrapolate that the only one who actually did number 1A on the homework is that guy Alex, who came to office hours, because I think he's the only one that kind of remembered this. But now all of you should be able to do number 1 on the homework. N is the number of units used, okay? And Buckingham said number of pi groups. So pi groups, he calls those dimensionless groups, is equal to what?
M minus n.
M minus n. All right, so how many, in this case, what is the number of variables here?
5 minus 2.
Yeah, 5 and 2. So we got, we got 3 pi groups?
Is that independent variables or all variables?
No, units. We do have 2 units. 1, 2, 3, 4, 5. Okay. All right. I get only 2 groups, so let's revisit this in a second. Probably something happened. All right, so first of all, so what are the possible groups? Pi 1, we said pi 1 was u over v. So Buckingham's doesn't tell you, so that's as far as Buckingham goes. It only tells you how many groups you're going to get. And the rest of it, you've got to figure out yourself by basically kind of, in this case, you can kind of, I would call it inspection, but you just see. Physically, what I do is I say, okay, so if once you have pi 1, you've used up u and v. So that means you don't have to use them again, because Buckingham says each variable has to appear, it should appear at least once. And usually the way it is, a lot of them are at most once. So if I use the two velocities, but then I have to use these three in a group. So how do I do that? Well, I think about, let's say I put nu in the denominator. Nu, it's got a length squared over time. How do I cancel that out with y and t, which are the variables I got left? Y squared divided by t. Okay. And this is a kind of a special, so if you think about it this way, if you're looking for a third group, it's not possible because you've kind of used all the variables already. And if you think about it, the reason why is because u and v already had the same units in the first place. So in some ways, m was equal to, let's say m was equal to basically 4, and n was equal to 3, because you had like two things at the same number. So that's why we had, 5 and 4 and 2.
If we take Reynolds number with length scale as y, then that is also non-dimensional. V y by nu.
Yeah, that's true. But we don't actually use Reynolds number in this problem. Here, let's just write pi 3 for the Reynolds number. And that would be velocity times length over nu. So nu, velocity, we're going to get y squared over time. But that's exactly the same thing as we got already. We already have a Reynolds number. Okay. So I think it's because these two have the same units, or these two are not independent units. They kind of have the same thing already. So I think it's because you have m equals 4 and you have n equals 2. So there's basically two independent groups. That's what I think. All right. So there are two dimensionless groups, and for reasons that will become apparent, basically, to make the algebra nice, I think people started with maybe these Reynolds numbers, but because we're going to do a bunch of algebra, people said, "Oh, let's just rewrite this." They're going to make pi 2 look like the following. To reduce algebra, we're going to write pi 2 as basically the square root of pi 2. So it's going to look like this, where we have c as a constant. And clearly, if pi 2 is dimensionless, taking the square root of it is going to be dimensionless too. And this is called the similarity variable. Okay. Similarity variable. All right, so Buckingham theorem tells you that you got those two pi groups because of your number of variables and number of units, but also tells you how they behave with respect to each other. So Buckingham also says, and if you don't know Buckingham, you can look at that lecture I have on, I think I have a lecture from my undergrad class I put on the syllabus, or you can just look at Wikipedia.
It is, it's there, where you talk about dimensionality.
Yeah. But they banned Wikipedia from my kid's school, actually, because they said,
they're starting to do disinformation in it.
yeah, they said that it's not like an encyclopedia because there's some things that are not correct in there. But I haven't found anything that's not correct, but I'm sure there's something in there. Okay, Buckingham says, hey, if you've got two dimensionless groups, one is a function of the other. So in this case, u over v is a function of the similarity variable, what we'll call eta. So let's call it eta from now on because it's really awkward to write this subscript. So we're going to try to solve, instead of solving the problem u as a function of all those variables, we're going to solve this dimensionless u as a function of eta. okay, remember the units of nu were length squared over time. So you could argue that basically square root of nu t is a length scale. And people actually have a word for this. This is called the diffusion length scale. Diffusion length scale. Okay. And then that means eta is basically the dimensionless distance from the lower boundary, right? Because it's y divided by square root of eta, not eta, nu t. Okay. All right, now the part that we have to do together is we need to, so in similarity solutions, all right, they're assuming this. This comes out of a separate fact from Buckingham's theorem. We need to re-express the whole equation in terms of eta, which is a new variable. So right now that PD is expressed to here. So the big picture is this. We're gonna get a so big picture. We have a PDE. The PDE was du dt is equal to nu d squared u dy squared. This is going to become an ODE. And we're going to figure out what that is. And from this, what we call the similarity transform, which is just a fancy word for we're going to write it in terms of eta instead of u, y, and t. And the three conditions that we had, which were one initial condition, two boundary conditions, are going to have to collapse. Because one of them is going to collapse to one condition. And we're going to get two boundary conditions. Because remember, because we have a similarity variable that has t in it, we don't really have like a time-dependent problem anymore. We consider it to be like a boundary. And basically what looked like this before, x, so it would look like this before. So this was x and y, and we said basically you got this information going out. It's going to look like this. We're going to have a function of eta, and this is going to have a function of u of eta. And it's going to be basically the solution is going to be a single curve. Okay, so that's basically the big idea of what we're going to do. So let's do this similarity transform together. I think and this is what I recommend for the homeworks. I'm glad that I think Ethan had started the several study groups. You should each have little stops, places that you stop in the problem that you check with your neighbors, make sure what you have is correct. Because there's nothing sadder than doing like 3 hours of algebra on something that's not even correct. So I would say, at medium points to the problem, say, hey, did you get this? And if you all got the same thing, hopefully you're all right. All right, so let's do this together. So we need to translate this thing into a derivative with respect to eta. So this is what I suggest you do. We have u is equal to nu f of eta, right? I just multiplied it by eta on both sides. Now we have eta is equal to y over square root of c nu t. Now we got to compute derivatives, okay? Because think about it, I'm going from this PDE, that has t and y. I've got to have everything to be a function of eta. So I would suggest you do these at your seats. If this is the case, calculate d eta dy and d eta dt. And then when you're done with that, calculate du dt, du dy, and eventually d squared u dy squared. And we're going to compare all those two and basically change that ODE from substitution into into an equation with eta. Okay. Yeah.
Where does the constant come from? In the eta.
It comes from when the people that did this problem, they realized later that the math is going to be a lot easier if I put an arbitrary constant in there. And the thing about dimensionless groups is that it's still dimensionless multiplied by a constant. So it's just kind of a trick to make your life less hard. But it's fine because it's dimensionless groups can have a constant. And we'll find out what that constant is later. So at your seats, compute each of these, and let's see who can convert that PD into the right thing. And I'm going to go around. So everyone should just do that. No one needs a whiteboard or anything? You're fine? So start with the right-hand side and then go to the left-hand side. That's what I suggest. And I'll do a check-in. Like once people get it, we'll start writing stuff. So this bottom left terms you use from the left equation. The right terms you use the right equation. And you can talk to your neighbor. That's probably going to be more fun. Just regroup in like 2 minutes. Yep, that's right. Yeah.
Because that one's the test and then multiplied by. That's the bottom.
I would only do these after you've done the the two on the right.
So then it would just be chain rule.
D, eta, dt, and dy, because you need those to do the chain roll.
These two.
You need those to do the chain roll. Okay, and I would substitute for eta in here, because something looks like eta. Then it'll be this a function eta, and you can reduce the number of terms you have. All right. Let's take a stop here for a review. Everyone should have done. I think everyone got this correctly. So this, all right. So these are partial derivative signs because eta is a function of y and t. So it's linear with y. So we just have this, right? I think everyone got that. Now this will be a trick that you use for all. So this one, you got you can imagine everything is a constant except for the t, the negative 1/2. So therefore, you're going to get a negative 1/2 for that t, and everything else stays there, c nu, because this is basically like a constant, right? Because it's not changing the t, and you get t the negative 3/2, right? Except you don't want to write it like that because you want to make your life easier later. You want to substitute for eta. So you substitute for the eta, you should get this. This is eta over 2t. Right? This went to 3/2, which means you're dividing by t, and you times negative 1/2. All right, so that's one algebraic trick you want to do. And let's talk about this first one. People need to remember the chain rule. So we're saying dimensional analysis tells us that u is equal to a constant v times a function of eta, an unknown function. So the chain rule says, hey, if I want to take u, derivative of u with respect to t, first that v comes out. Actually, no, let's do that later. Just the general expression for this is, well, first I got to take u as a function of eta, and then I can take eta as a function of t, right? Because eta is a function of y and t. So this is what I got to do. And then now let's do this. Now du d eta, that's just v, because that's a constant. F, we'll call this df d eta. And then I take d eta as a function of t, which I can just copy from over here, which is negative eta over 2t. All right? All right. So see if you can do the similar trick for y and then the second derivative of that. All right. All right, so du dy, I'm going to do something similar. First I have du d eta, and I have d eta dy. All right. Du d eta is u df d eta, like above. Sorry, v. And d eta dy I copy from our right-hand side. So I have 1 over c nu t. Okay, and the second derivative with respect to y, now basically the only thing that I take the derivative of is this thing, because there's no y's in the other parts. So I got, let's put everything to the front, c nu t, and then I take basically d dy of f eta. All right, so I'm going to use this notation that df d eta is going to be f sub eta, okay, just to reduce the writing. This we got that by the chain rule again. And if we use what we have up there, this becomes a nice thing, c nu t times f eta. All right. So the similarity transform requires you to do 5 derivatives, and then we got to do something with those derivatives. We're going to substitute. So what the key thing was doing these left-hand side terms. But to get that left-hand side terms, I had to first do these right-hand side terms. And now these are exact terms that I have in my PDE. So I'm going to substitute for all of them and sub in PDE. So this term becomes the following: negative v eta over 2t f eta is equal to nu v c nu t f eta eta. Oops. Oh my gosh. F eta eta. Simplifying that, I get f eta eta plus c over 2 f 8. Okay, c over 2 times eta f eta is equal to 0. Voila. That's what we did all this work for, to basically get PDE into this ODE with our similarity variable. This is an ODE for f of eta. Now this is an ODE that we can solve. Let Q is equal to f eta, and that means this becomes Q eta plus C over 2 eta Q eta equals 0. I can write that as the derivative of the log Q equal to negative C over T eta d eta. And that means Q is equal to A e to the negative c over 4 eta squared. Yeah.
Is that supposed to be nu times q or nu times q?
Thanks. I think everyone's seen an ODE like this, right? There's just first order ODE with like a constant, and then basically we have this exponential term. All right, so now you see why we had that C up there. So basically, the mathematician said, hey, let's just set C equals to 4, so we don't have to carry around this 1 over 4 everywhere to simplify algebra. That means your Q is f eta, and that's equal to B e to the negative eta squared. All right. Now we solved for Q, but the whole problem was to solve for F. So now we got to integrate Q from 0 to eta. All right. By the fundamental theorem of calculus, if you remember, we got f eta d eta is equal to f of eta minus f of 0. So we got f of eta minus f of 0 is going to equal to the integral of q e to the negative s squared ds. This so now let's apply boundary condition 1. So this requires some interpretation because we had the boundary conditions written in our old units, our old variables. Y equals v at y equals 0, the no slip, that corresponds to f equals 1 at eta is equal to 0. Okay. Remember, f was the velocity. Remember, we had u is equal to f of eta. So if f is equal to f is just equal to 1 at basically y equals 0. And remember, eta was equal to y over square root of c nu t. Okay. So f, that function is just a constant function, and that's equal to 1 at y equals 0. Okay, so everyone, hopefully people see that. And therefore, my f of eta, I'm getting closer, 1 plus b, 0 of eta, e to the negative s squared ds. All right, now I'm getting something that looks like it's something I can deal with. Now, how do I solve for little b? Out of time. I won't make you suffer after class. We can, so this homework is going to be a separation of variable problem, which I think some of you learned before, for number 2. Number 3 is going to be like this, similarity solution. So, and number 4 is actually like undergraduate fluid mechanics. So I would start a little bit number 3. At least you'll be able to do this part, and I'll show you. Basically, f is going to be something called the complementing error function, which is like, it's kind of like sine and cosine for grad students. Have you guys ever heard of error function? It's like the integral of the Gaussian, but it occurs in physics because the Gaussian occurs everywhere. So we're going to get that out of here, and you're going to get that in the homework. But start this homework. There's like a lot of steps in this homework, so you got to spread it out. I wouldn't want to do it all the night before. Okay, we will have office hours for a little bit before the next class rolls in. Remember, we have a holiday next week, Monday and Tuesday, but grad students really don't have holidays. But at least we won't have class. The Institute holiday, it's like reducing student suicides and stuff like that. I think that's the unsaid motto. I think the deans did some statistical tests that if we have less school, people kill themselves less. So we have less and less school over time.
I have lots of questions, but I've got to go mess with this first so I understand which ones make any sense about it.